Imagine standing on Earth, looking up at our sun. It's so massive that you could fit 1.3 million Earths inside it. It's so powerful that every second, it converts 600 million tons of hydrogen into helium, releasing enough energy to power human civilization for 500,000 years. Now, what if I told you that compared to the largest star we've ever discovered, our sun is basically invisible? Not just smaller, not just dimmer. I mean, if you put them side by side in space, you wouldn't even see our sun. It would be like comparing a grain of sand to Mount Everest. Actually, no, that comparison makes Mount Everest seem too small. The largest star ever discovered is called Stephenson 2-18. And here's what will blow your mind. If you replaced our sun with this cosmic monster right now, its surface would extend past the orbit of Saturn. Think about that. Saturn is so far away that light from the sun takes over an hour to reach it. This single star is so incomprehensibly large that it would swallow Mercury, Venus, Earth, Mars, Jupiter, and Saturn whole, and still have room to spare. We would be living inside the star. But here's the thing that's going to haunt you for the rest of this video. We're not even entirely sure this is the largest star. There are candidates out there that might be even bigger. Stars so massive that our telescopes can barely comprehend them. Stars that challenge everything we thought we knew about how large a star can possibly get before it tears itself apart. And the most mind-bending part? These stellar giants are dying. They're in their final death throes. And when they go, they'll explode with such force that they'll briefly outshine entire galaxies containing hundreds of billions of stars. Before we dive deeper into this cosmic nightmare of scale, do me a favor. Smash that like button, hit subscribe, and let me know in the comments, what country are you watching from? And what time is it where you are? I want to see how far across the globe this journey into the incomprehensible is reaching. Now, let's begin. To understand just how disturbing Stephenson 2-18 really is, we need to start with something familiar and work our way up. Let's begin with Earth. Our planet has a diameter of about 12,742 kilometers. It feels massive to us because we can never truly comprehend its full size in a single glance. But in cosmic terms, Earth is a speck. Now, let's scale up. Jupiter, the largest planet in our solar system, is about 11 times wider than Earth. You could fit 1,321 Earths inside Jupiter. When you look at Jupiter through a telescope, you're seeing a world so large that its Great Red Spot Storm is bigger than our entire planet. That storm has been raging for at least 400 years, possibly much longer. Think about that. A single weather system larger than Earth, persisting for centuries. But Jupiter is still just a planet. Let's talk about our sun. The sun is 109 times wider than Earth. Its diameter is 1.4 million kilometers. If Earth were the size of a basketball, the sun would be about 24 meters wide, roughly the size of a small house. The sun is so massive that it contains 99.86% of all the mass in our entire solar system. Everything else, all the planets, all the asteroids, all the comets, all the dust, makes up less than 0.14%. Think of it like this. Imagine you have a large room filled with 1,000 basketballs. The sun is 986 of those basketballs. Jupiter is about 10 basketballs. Everything else we know, Earth, Mars, Venus, you, me, every mountain, every ocean, every human who has ever lived fits into the remaining 4 basketballs. That's our cosmic significance. Here's where it gets interesting. Our sun is actually a pretty average star. Astronomers classify it as a G-type main sequence star, or a yellow dwarf. It's medium-sized, medium temperature, medium everything. It's the Honda Civic of stars, reliable, common, nothing special. There are billions of stars just like it in our galaxy alone. But stars come in wildly different sizes. On the small end, you have red dwarf stars that might be only 7.5% the size of our sun. Some red dwarfs are barely larger than Jupiter, just massive enough to sustain nuclear fusion in their cores. On the opposite extreme, you have hypergent stars so massive that they make our sun look like that grain of sand I mentioned earlier. The first hypergent that really captured human imagination was discovered in 1860 by a German astronomer named Friedrich Wilhelm August Argelander. He was cataloging stars when he noticed something strange, a star that varied dramatically in brightness over time. This star was Betelgeuse, and it's one you might actually recognize because it's visible to the naked eye. It's the bright reddish star forming the shoulder of the constellation Orion. In 1920, a physicist named Albert Michelson became the first person to measure the diameter of a star other than the Sun. Using a technique called interferometry at the Mount Wilson Observatory, he measured Betelgeuse. What he found was shocking. Betelgeuse was approximately 700 times larger than our Sun. If you put Betelgeuse where our Sun is, its surface would extend past the orbit of Mars. Earth would be incinerated, vaporized, and consumed inside this stellar monster. For decades, Betelgeuse held the record as one of the largest known stars. But as our telescopes improved and we looked deeper into the cosmos, we found even larger stars. Here's what's going to mess with your head. The bigger these stars get, the stranger they become, and the physics governing them starts to border on the impossible. Let's do something right now that might break your brain a little bit. I want you to imagine you're an astronaut in a spacecraft approaching Betelgeuse. You're starting from the distance where Earth orbits our Sun 93 million miles away. At this distance from Betelgeuse, you're already inside the star. The star's outer atmosphere surrounds you. But here's the thing, you wouldn't really notice. The outer layers of these red supergiants are so diffuse, so spread out, that the density is actually lower than the best vacuum we can create on Earth. You'd keep traveling inward, and for days, weeks, maybe months, depending on your speed, you'd see almost nothing change. Just a gradually brightening reddish glow around you. This is the disturbing part about these stellar giants. They're mostly empty space. All that mass hundreds of times more massive than our Sun is spread across a volume so large that most of the star is less dense than air. Eventually, as you got closer to the core, things would get weird. The temperature would skyrocket. The density would increase. And finally, you'd reach the core, where temperatures soar to millions of degrees and nuclear fusion is creating new elements. But to get there from the surface would take longer than flying from the Sun to Earth multiple times. Now, here's where our journey into the truly incomprehensible begins. In 1860, a British astronomer named Joseph Baxendale discovered a star that would change everything. He was conducting a survey of stars when he noticed an extremely faint object in the constellation Cepheus. This star was catalogued as HD 190,390, but it would later become famous by another name, Mu Cephei, or Herschel's Garnet Star. When astronomers finally measured Mu Cephei in the 20th century, they found something disturbing. This star was 1,260 times larger than our Sun. If you replaced our Sun with Mu Cephei, its surface would extend beyond the orbit of Jupiter. Think about that. Jupiter orbits at 778 million kilometers from the Sun. This single star's radius is larger than that entire distance. But we weren't done finding monsters. In the 1970s, using improved spectroscopy and interferometry techniques, astronomers started finding even larger stars. Canis Majoris was discovered to be approximately 1,420 times larger than the Sun. Then we found Scuti, estimated at about 1,708 solar radii. Each discovery pushed the boundaries of what we thought was physically possible. You see, there's a problem with these ultra-massive stars. They shouldn't exist, or at least they shouldn't be stable. A star is a constant battle between gravity trying to crush everything inward and the outward pressure from nuclear fusion trying to blow everything apart. For our Sun, this balance is pretty stable. The sun will maintain this balance for about 10 billion years total. It's currently about 4.6 billion years old, so it's got about 5.4 billion years left. But these hypergeans are different. They're so massive and so energetic that they're incredibly unstable. Their outer layers are being blown off into space constantly by powerful stellar winds. They pulsate, expanding and contracting. Some of them vary in brightness by several magnitudes over periods of months or years. They're basically giant cosmic wobbles, stars that are barely holding themselves together. Here's a thought experiment for you. Imagine you could compress all of Earth's matter into a ball the size of a marble. That marble would weigh 6 trillion kilograms. The entire mass of Earth is something you could hold in your hand. The gravity at the surface of that marble would be so intense that it would kill you instantly, crush you into atoms, maybe even crush your atoms into neutrons. Now imagine something with hundreds of times more mass than our sun, spread across a volume 1 billion times larger. The internal structure of these stars is so alien to our everyday experience that it challenges our basic intuition about how matter and gravity work. What if I told you that we've found stars even larger than you? Why, Scotty? Stars that push the theoretical maximum limit for how large a star can possibly get? In 1990, 2 astronomers named Charles Bruce Stevenson and Nicholas Sage-Leck published a survey of open star clusters. One of these clusters, designated Stevenson 2, was located about 19,000 light-years away in the constellation Scutum. This cluster contained several notable red supergiant stars, but one of them would eventually claim the title as the largest known star in the universe. Stevenson 2 to 18, as it came to be known, didn't immediately reveal its true size. Measuring the diameter of distant stars is extraordinarily difficult. Unlike planets in our solar system, which we can see as disks through telescopes, stars are so far away that even the largest ones appear as point sources of light. To measure their size, astronomers use clever indirect methods, studying the star's spectrum, measuring how it blocks light from background stars, analyzing its brightness variations, and using interferometry to combine light from multiple telescopes. When astronomers finally calculated the size of Stevenson 2 to 18 using these techniques, they found something that seemed almost impossible. This star has a radius approximately 2,150 times that of our sun. Let me put that in perspective, because numbers this large become meaningless without context. If you placed Stevenson 2 to 18 at the center of our solar system, where the sun currently sits, its surface would extend to approximately 2.9 billion kilometers from its center. Saturn orbits at about 1.4 billion kilometers from the sun. This means Stevenson 218's surface would extend more than twice as far as Saturn's orbit. In fact, it would nearly reach the orbit of Uranus, which circles the sun at about 2.9 billion kilometers. Think about that journey. When Voyager 2 flew past Saturn in 1981, it had been traveling for 4 years since its launch. It would take another 8 years before it reached Uranus. The distance from the sun to Uranus is so vast that light traveling at 300,000 kilometers per second, the fastest thing in the universe, takes nearly 3 hours to cross it. And this single star is that large. Here's another way to visualize it. If you could drive a car at highway speeds, 100 kilometers per hour, in a straight line from one side of Stevenson 2 to 18 to the other, passing through its center, it would take you about 6,640 years to complete the journey. That's longer than all of recorded human civilization. The ancient Sumerians invented writing around 3200 BCE, about 5,200 years ago. You could have started driving when they invented writing, driven every single day for their entire civilization, through ancient Egypt, ancient Greece, ancient Rome, the Middle Ages, the Renaissance, the Industrial Revolution, both world wars, the space age, right up to today, and you still wouldn't have crossed this star. But here's what really messes with your mind. Despite being 2,150 times larger than our sun, Stephenson 2 to 18 is only about 14 times more massive. How is that possible? How can something so much larger be only 14 times heavier? The answer is density. Remember when I said these hypergents are mostly empty space? Stephenson 2 to 18 is the ultimate example. The Sun has an average density of about 1.4 grams per cubic centimeter, slightly denser than water. Stephenson 2 to 18 has an average density millions of times lower. If you could scoop out a cubic meter of material from the outer layers of Stephenson 2 to 18, it would weigh less than the air in your room. In 2018, a team of astronomers led by Ben Davies of Liverpool John Moores University conducted a comprehensive study of the Stephenson 2 cluster. They used advanced spectroscopic techniques to measure the properties of its stars more accurately. Their findings confirmed that Stephenson 2 to 18 was indeed one of the largest stars known to science, though they acknowledged significant uncertainty in the measurements. The true radius could be anywhere from about 1,900 to 2,400 solar radii. This uncertainty bothers astronomers. We've found this cosmic giant, but we can't pin down its exact size. That's because Stephenson 2 to 18 is surrounded by a thick envelope of dust and gas that it's actively blowing off into space. This material obscures our view and makes measurements difficult. It's like trying to measure the size of a building while it's shrouded in thick fog. Here's what will blow your mind. If Stephenson 2 to 18 were suddenly transported to where our Sun is, replacing it instantly, we wouldn't see the Sun disappear. We'd see it transformed into a vast, reddish wall that would fill our entire sky. Except we wouldn't see it for long, because we'd be inside it. Earth would be orbiting inside the star's outer atmosphere, experiencing temperatures of thousands of degrees. Our planet would be vaporized within hours, maybe days. But there's something even more disturbing. Stephenson 2 to 18 might not even be the largest star. Science loves a good controversy, and the question of which star is truly the largest has sparked intense debate among astronomers. The problem is that measuring these stellar monsters is incredibly difficult, and different measurement techniques can give wildly different results. Let me introduce you to some of the contenders for the largest star title. Each one has its champions and skeptics, and each one reveals something profound about the limits of stellar physics. First, there's VV Cephei, discovered in the constellation Cepheus. This is actually part of a binary star system, two stars orbiting each other. The larger of the two, VV Cephei, is a red supergiant with an estimated radius of about 1,050 to 1,900 solar radii, depending on which study you believe. What makes VV Cephei particularly interesting is that we can actually watch its companion star pass behind it during eclipses, giving us another way to measure its size. These eclipses last for years, yes, years, because the star is so large. Then there's Astronomy, a variable star that pulsates dramatically. Some estimates put its maximum radius at around 1,500 to 1,700 solar radii. The challenge with Astronomy is that it's constantly changing size as it pulsates. Do we measure it at its largest, its smallest, its average? Each choice gives a different answer. My personal favorite is KY Cygni, located about 5,000 light years away. In 2008, a team led by Emily Levesque at the University of Hawaii estimated its radius at approximately 1,420 solar radii, but with enormous uncertainty bars. Other studies have suggested it could be as large as 2,850 solar radii, larger than Stephenson 2 to 18. But the data is messy, contradictory, and frustratingly imprecise. Here's where it gets philosophically interesting. What does it even mean to ask which star is largest? These hypergents don't have well-defined surfaces the way planets do. If you were approaching Earth from space, there would be a clear boundary where the vacuum of space ends and the atmosphere begins. But hypergent stars have such diffuse outer atmospheres, that the transition from star to not star is gradual and fuzzy. Where exactly do you draw the line and say, this is the surface? Different astronomers define the stellar surface differently. Some use the photosphere, the layer where the star becomes opaque to light. Others use the point, where the density drops below a certain threshold. These different definitions can lead to different size measurements for the same star. In 2012, a team of astronomers led by Ariane Lankan at the Strasbourg Observatory tried to tackle this problem systematically. They developed a standardized method for measuring red supergiant radii using infrared observations and modeling. Their work helped resolve some discrepancies, but it also revealed just how uncertain our measurements really are. For many hypergeans, the margin of error in the radius measurement is larger than the entire radius of our sun. But here's the really mind-bending part. There might be stars out there even larger than any we've measured, stars so deeply shrouded in dust, or so far away, or so faint, that we simply haven't detected them yet. Our galaxy alone contains an estimated 100 to 400 billion stars. We've carefully studied maybe a few million of them. What monsters might be lurking in the unexplored reaches of the Milky Way? In 2020, astronomers discovered something called red nova events, cosmic explosions that occur when two stars in a binary system merge. Some models suggest that these mergers could temporarily create stars even larger than Stephenson 2 to 18, perhaps reaching 3,000 or even 4,000 solar radii before the merged star settles into a new configuration or explodes. These would be temporary giants, existing for maybe just a few years or decades, but they would be the largest stellar objects in the universe during their brief lifetimes. And then there's the theoretical maximum. According to our current understanding of stellar physics, there's a limit to how large a star can get before it becomes unstable and tears itself apart. This limit is called the Eddington limit, named after the British astrophysicist Arthur Eddington, who worked it out in the 1920s. The Eddington limit occurs when the outward pressure from radiation becomes so intense that it overcomes gravity and starts blowing the star's outer layers away faster than gravity can hold them. For the most massive hypergeans, we're right at this limit. They're teetering on the edge of physical possibility, held together by the thinnest margin. And here's what that tells us. We might already have found the largest stars that can physically exist. Stephenson 2 to 18 and its competitors might be as large as stars can possibly get in our universe. We might be living at a time when we can observe the cosmic size limit for stars. Think about how special that is. Of all the possible moments in the 13.8 billion year history of the universe, we happen to exist right now, with technology just advanced enough to detect these ultimate stellar giants. That's either an incredible coincidence, or it tells us something profound about our place in cosmic history. Now, let's talk about why these stars are so weird and why they challenge our understanding of physics. To do this, we need to understand how stars work at a fundamental level. A star is born when a cloud of hydrogen gas collapses under its own gravity. As the gas falls inward, it compresses and heats up. Eventually, the core becomes so hot and dense around 10 million degrees Celsius that hydrogen atoms start fusing together to form helium. This nuclear fusion releases tremendous energy, creating an outward pressure that balances the inward pull of gravity. The star reaches equilibrium and settles into what astronomers call the main sequence, where it will spend most of its life steadily burning hydrogen. Our sun is in this phase right now and will remain there for billions of years. It's a comfortable, stable existence. But that stability depends on having just the right amount of mass. Too little mass, and you can't get hot enough to start fusion. You end up with a brown dwarf, a failed star. Too much mass, and things get complicated. The stars that eventually become hypergeans like Stephenson 2 to 18 start their lives very differently. They're born with 20, 30, maybe 40 times the mass of our sun. With that much mass, the gravitational pressure in the core is immense. The core temperature soars not to 10 million degrees, but to 30 or 40 million degrees. Fusion proceeds at a furious rate. Here's the crazy part. Even though these massive stars have much more fuel than the Sun, they burn through it much faster. A star with 40 solar masses might only live for a few million years, a cosmic eye blink, compared to the Sun's 10 billion-year lifespan. They live fast and die young. As these massive stars age, they go through a series of dramatic transformations that our Sun will never experience. When they exhaust the hydrogen in their cores, they start fusing helium into carbon. Then they fuse carbon into neon, neon into oxygen, oxygen into silicon. Each stage happens faster than the last and requires higher temperatures. The star develops an onion-like structure, with different elements being fused in different layers. During these later stages of fusion, something remarkable happens. The star expands dramatically. A star that might have started its life only 10 or 20 times larger than the Sun can swell to hundreds or thousands of solar radii. The outer layers cool as they expand, giving the star the characteristic red color. It becomes a red supergiant. But here's what's deeply weird. As the star expands, its surface gravity decreases. Remember, gravity depends on mass and distance. Even though the star's total mass hasn't changed much, the distance from the core to the surface has increased dramatically. At the surface of Stephenson 2 to 18, the gravitational acceleration is estimated to be only about 0.003% of what we experience on Earth. That's essentially zero. An astronaut standing on the surface, if there were a solid surface to stand on, would weigh almost nothing and could jump into space with minimal effort. This creates a bizarre situation. The outer layers of the star are barely held on by gravity. Meanwhile, the star's luminosity has increased dramatically. Stephenson 2 to 18 is about 440,000 times more luminous than our Sun. All that energy flowing outward creates radiation, pressure literally pushing on the star's outer layers with the force of photons. The result is that these hypergions are constantly blowing off their outer layers in powerful stellar winds. Stephenson 2 to 18 is losing mass at a rate of about 1 Earth mass every 6,000 years. That might not sound like much, but over the star's lifetime, it will lose a significant fraction of its total mass. It's literally falling apart as we watch. In 1935, an Indian-American astrophysicist named Subramanian Chandrasekhar calculated that there's a maximum mass for white dwarf stars, about 1.4 solar masses, now called the Chandrasekhar limit. Above this mass, a white dwarf can't support itself and will collapse. There are similar limits for other types of stars and stellar remnants. For hypergions, the limit isn't about mass, but about luminosity and radius. When a star gets large enough and bright enough, the radiation pressure pushing outward overwhelms gravity. The star becomes unstable. It might eject huge amounts of mass in eruptions. It might pulsate violently. Eventually, it will destroy itself. Some astronomers believe we're watching this process happen in real time with stars like Betelgeuse. In 2019 and 2020, Betelgeuse dimmed dramatically, losing more than 60% of its brightness. At first, astronomers thought it might be about to go supernova, the explosive death of a massive star. Further observations revealed that Betelgeuse had ejected a huge cloud of dust that was temporarily blocking our view. The star had essentially coughed up part of itself. Could the same thing happen to Stephenson 2 to 18? Absolutely. In fact, it's probably happening constantly, just on a scale we can barely detect from 19,000 light years away. Here's the existential question this raises. Are we really observing stable stars? Or are we watching objects in their final death throes? Cosmic organisms that are falling apart even as we study them? And if these are dying stars, what does that tell us about the life cycle of the universe itself? Let's do something that might permanently alter how you think about space and scale. I want to take you on a journey through Stephenson 2 to 18, from the outer surface to the core, and I want you to really try to grasp the distances involved. We're going to start at the surface, or at least what astronomers define as the photosphere, the layer where the star becomes opaque. You're in a spacecraft, looking around. In every direction, all you see is a faint reddish glow. The material around you is incredibly diffuse, less dense than Earth's atmosphere at 100 kilometers altitude, which is essentially space. But it's hot several thousand degrees. Your spacecraft's shields are doing most of the work, keeping you alive. You start traveling inward toward the core at 1,000 kilometers per second. That's fast. It's about 0.3% the speed of light. At this speed, you could travel from Earth to the Moon in less than 7 minutes. You could cross the entire diameter of Earth in less than 13 seconds. How long do you think it would take to reach the core of Stephenson 2 to 18 traveling at this speed? Try to guess before I tell you. The answer is approximately 56 days. Let that sink in. Traveling at 1,000 kilometers per second, a speed that would get you from New York to Los Angeles in 4 seconds. It would take you almost 2 months to reach the center of this star. For nearly 2 months, you'd see almost nothing change, just a gradual increase in temperature and density. The same reddish glow, slowly brightening. Think about what that means. This isn't science fiction hyperbole. This is the actual geometry of this object. It's so large that our human brains literally cannot comprehend it. We can calculate it, we can visualize it mathematically, but we cannot truly, intuitively grasp it. Here's another way to think about it. Light travels at 299,792 kilometers per second. Nothing in the universe goes faster. Light from Stephenson 2 to 18's core takes about 2.5 hours to reach the surface. For comparison, light from the sun's core takes only 2.3 seconds to reach the surface. Well, actually, that's not quite right. Light from the sun's core takes thousands of years to reach the surface because it keeps bouncing around inside. But the direct distance could be crossed in 2.3 seconds if the light could travel in a straight line. Now imagine this. Every second, Stephenson 2 to 18 is producing about 440,000 times more energy than our entire sun. That energy is being generated in the core through nuclear fusion. But it takes hours for that energy to travel from the core to the surface and radiate into space. At any given moment, the star contains hours' worth of energy production trapped inside it, slowly working its way outward. The volume of Stephenson 2 to 18 is approximately 10 billion times the volume of our sun. If you could somehow count every cubic meter inside this star, 1 cubic meter per second, it would take you 317 years to finish counting. Let's try another thought experiment. Imagine you could fill Stephenson 2 to 18 with Earth-sized planets, packing them in as efficiently as possible. How many do you think would fit? The answer is approximately 6.5 billion Earths. That's almost 1 planet for every person currently alive on Earth. If every human being alive today owned their own personal Earth-sized planet, and we packed all those planets together, they would roughly fill the volume of Stephenson 2 to 18. Or think of it this way. If you shrank the sun down to the size of a marble, Stephenson 2 to 18 would be a sphere about 46 meters in diameter, the height of a 15-story building. At that scale, Earth would be invisible to the naked eye, smaller than a grain of sand. But here's what really messes with my head. Despite being so incredibly large, Stephenson 2 to 18 is not the most massive star. That title belongs to stars like R136A1, a blue hypergent with about 315 solar masses. R136A1 is only about 30 times larger than the Sun in radius tiny compared to Stephenson 2 to 18, but it's 23 times more massive than Stephenson 2 to 18, packed into a much smaller volume. This reveals something profound. In the universe, size and mass don't correlate the way we intuitively expect. The largest things aren't necessarily the heaviest. A red supergiant like Stephenson 2 to 18 is like a cosmic balloon, huge in volume, but relatively light. A blue hypergent like R136A1 is like a cosmic cannonball, relatively compact, but incredibly heavy. And both of them are doomed. Both are burning through their nuclear fuel at prodigious rates. Both will die in spectacular supernova explosions. In fact, they might already be dead. Remember, Stephenson 2 to 18 is 19,000 light years away. We're seeing it as it was 19,000 years ago. If it exploded 10,000 years ago, we won't know for another 9,000 years. That's the final mind-bending aspect of astronomical observation. We're always looking into the past. When we observe these distant stellar giants, we're seeing ancient history. We're time travelers, studying objects that may no longer exist. Now we need to talk about what happens when these monsters die, because their deaths are just as extraordinary as their lives, and they have profound implications for everything in the universe, including us. When a star like our sun runs out of fuel, it will expand into a red giant, then gently shed its outer layers, leaving behind a white dwarf, a dense, Earth-sized remnant that will slowly cool over trillions of years. It's a relatively peaceful death. Hypergiants die differently. They die violently. When a star like Stephenson 2 to 18 exhausts all its nuclear fuel, the core suddenly has nothing to support it against gravity's crushing force. In less than a second, literally in the time it takes you to blink, the core collapses from something the size of Earth to something the size of a city. In that fraction of a second, matter is compressed to densities that exceed anything else in the universe, except black holes. The collapse releases a staggering amount of gravitational energy. So much energy that it reverses the infall and sends a shock wave blasting back outward through the star. This shock wave tears through the star's layers at tens of thousands of kilometers per second. When it reaches the surface, the star explodes in what we call a supernova. For a few weeks, a single supernova can outshine an entire galaxy containing hundreds of billions of stars. Let me repeat that. One star, one exploding star, can briefly be brighter than 100 billion normal stars combined. The energy released in a supernova is about YY joules. That's a 1 followed by 44 zeros. In comparison, the sun's total energy output over its entire 10 billion year lifetime is about 1,043 joules. A supernova releases 10 times more energy in a few seconds than the sun will produce in its entire existence. In 1987, astronomers witnessed a supernova in a large Magellanic Cloud, a small galaxy near our own. This event, designated SN1987A, was studied by astronomers including Stan Woosley at UC Santa Cruz and Adam Burrows at Princeton. Even though SN1987A was 168,000 light years away, it was visible to the naked eye. Neutrino detectors on Earth actually detected neutrinos from the supernova ghostly particles that passed right through the Earth. About 25 neutrinos were detected out of the 1,058 neutrinos the supernova produced. Think about that number, 1058 neutrinos. That's a billion neutrinos. The supernova flooded the entire region of space with neutrinos. Some of those neutrinos passed through your body if you were alive in 1987. They passed through the Earth, through the sun, through everything, barely interacting with anything. Most neutrinos from SN1987A are still traveling through space right now, spreading outward in an ever-expanding shell. When Stephenson 2 to 18 goes supernova, it will be even more spectacular. The explosion will eject the star's outer layers, multiple solar masses of material, into space at significant fractions of the speed of light. This material will form an expanding nebula, enriching the surrounding space with heavy elements created in the star's core and in the supernova explosion itself. Here's something profound. Almost every element heavier than helium in your body was created inside a star. The carbon in your DNA, the iron in your blood, the calcium in your bones, all of it was forged in stellar cores and scattered into space by supernova. You are literally made of stardust. And that's not a poetic metaphor. That's the literal scientific truth. But there's more. When Stephenson 2-18 dies, what's left behind? After the explosion, after all that violence, what remains? For a star of Stephenson 2-18's mass, the core will collapse into one of two things, either a neutron star or a black hole. A neutron star is an object about 20 kilometers across, but containing more mass than our entire sun, compressed to densities where atoms are crushed and matter exists in forms we can barely comprehend. A black hole is even stranger, a point in space where gravity is so intense that nothing, not even light, can escape. In 2017, astronomers made a discovery that shook the foundations of astrophysics. They detected gravitational waves, ripples in space-time itself, from the collision of two neutron stars. This event, designated GW170817, was studied by thousands of astronomers worldwide, including teams led by Ido Berger at Harvard and Eleonora Troja at NASA. When neutron stars collide, they create heavy elements like gold and platinum through rapid neutron capture. The amount of gold created in this single collision was estimated to be about 10 Earth masses worth. This is how the universe makes its heaviest elements. Not in ordinary stellar cores, but in the violent deaths and collisions of the most massive stars. Every gold ring, every platinum catalyst, every element heavier than iron, all of it was created in catastrophic cosmic events. When Stephenson 2-18 explodes, it will forge new elements and scatter them into space. Someday, billions of years from now, those elements might become part of new planets orbiting new stars. Maybe even planets with life, with civilizations, with beings who look up at their night sky and wonder about the universe. In a very real sense, Stephenson 2-18's death will give birth to new worlds. The end of this stellar giant will be the beginning of countless new stories in the cosmos. I want to pause here and recalibrate your sense of where we are in all of this, because understanding the largest star in the universe means understanding our own cosmic context. Earth orbits the Sun at a distance of about 150 million kilometers, a distance we call 1 astronomical unit, or 1 astronomical unit. The Sun sits in a relatively quiet region of the Milky Way galaxy, about 26,000 light-years from the galactic center. We're located in a minor spiral arm called the Orion Spur, a small branch off one of the galaxy's major spiral arms. The Milky Way itself is a barred spiral galaxy containing somewhere between 100 and 400 billion stars. It's about 100,000 light-years in diameter. If you could shrink the Milky Way down until the Sun was the size of a blood cell, the galaxy would be about the size of the United States. In this scale model, Stephenson 2-18 would be somewhere in Kansas, and we'd be in New York. Our galaxy is part of the local group, a collection of about 80 galaxies bound together by gravity. The Milky Way and Andromeda are the two largest galaxies in the local group. The entire local group spans about 10 million light-years. The local group is part of the Virgo supercluster, which contains about 100,000 galaxies. And the Virgo supercluster is part of Laniakea, an even larger structure containing 100,000 galaxies spread across 520 million light-years. And all of this, the Earth, the Sun, Stephenson 2-18, the Milky Way, the local group, the Virgo supercluster, Laniakea, all of it is just a tiny corner of the observable universe, which spans about 93 billion light-years and contains an estimated 2 trillion galaxies. Here's the thing that's going to mess with you. Stephenson 2-18, despite being the largest known star, is still just one star among trillions upon trillions. In the grand scheme of the cosmos, it's insignificant. But from our perspective, from our tiny rocky planet orbiting an ordinary yellow dwarf in a quiet arm of an average spiral galaxy, Stephenson 2 to 18 represents the absolute extreme of what nature can create. We're living in a universe that can produce objects so large they strain our comprehension. Objects that exist at the very edge of physical possibility. And we're living at precisely the right moment in cosmic history to observe them. Think about that timing. The universe is 13.8 billion years old. In another trillion years, all the stars will have burned out, and the universe will be dark and cold. We exist in the first 1% of cosmic history, during the brief epoch when stars are burning brightly. And not only that, but we exist at the exact moment when our species has developed technology sophisticated enough to detect these distant stellar giants. In 1990, the Hubble Space Telescope was launched. In 1995, Michel Mayor and Didier Queloz discovered the first planet orbiting another sun-like star, opening the field of exoplanet research for which they later won the Nobel Prize. In the past few decades, we've discovered thousands of planets around other stars, detected gravitational waves, imaged black holes, and measured the composition of atmospheres on planets light years away. We're living through a golden age of astronomy, a brief window of time when we can peer deeper into the cosmos than ever before. But before light pollution, atmospheric changes, or societal collapse potentially rob us of that ability. And in this golden age, we found Stephenson 2 to 18. We found the limit of stellar size. We've touched the boundary of what's possible. But here's the philosophical question that haunts me. Why do we care? We will never visit Stephenson 2 to 18. We will never even see it with the naked eye. It's far too distant and obscured by dust. Humanity will almost certainly go extinct long before Stephenson 2 to 18 goes supernova. So why does it matter? I think it matters because it tells us something about the universe we inhabit. It tells us that we live in a cosmos capable of producing wonders beyond imagination. It tells us that the universe is stranger, more varied, and more extreme than we ever expected. Every time we think we've found the limit, the biggest star, the most massive black hole, the oldest galaxy, we discover something that pushes that limit further. The universe is not static. It's not finished. It's an ongoing experiment in what's possible. And we're privileged witnesses to that experiment. Let me take you through the entire life story of a star like Stephenson 2 to 18, from birth to death, because understanding its life cycle reveals something profound about how the universe creates complexity. About 5 to 10 million years ago, a cosmic eye blink, a giant molecular cloud in what would become the Stephenson 2 cluster began to collapse. These molecular clouds are vast, containing enough material to create thousands of stars. They're mostly hydrogen gas, with a sprinkling of heavier elements, the remnants of previous generations of stars that lived and died. Within this cloud, a denser region began to contract under its own gravity. As it contracted, it fragmented into smaller clumps, each clump destined to become a star. One of these clumps was special. It contained about 20 to 40 solar masses of material, far more than most clumps. Over the course of perhaps 100,000 years, this massive clump collapsed. The center heated up as gravitational potential energy converted to thermal energy. Eventually, the core temperature reached 10 million degrees and hydrogen fusion ignited. A new star was born, a massive blue, incredibly bright O-type star. At this early stage, Stephenson 2 to 18, though it didn't have that name yet, of course, was nothing like the red supergiant we see today. It was probably only about 20 to 30 solar radii large, but not extraordinarily so. Its surface temperature was around 30,000 degrees Celsius, giving it a brilliant blue-white color. It was pumping out vast amounts of ultraviolet radiation, ionizing the gas around it and creating beautiful nebulae. For several million years, the star burned hydrogen steadily in its core. This was its main sequence phase, though even on the main sequence, it was living at a furious pace. A star with 40 solar masses burns through its hydrogen in about 1 million years. compared to the sun's 10 billion years. It's like comparing a high-performance sports car that burns through a tank of gas in an hour to an efficient sedan that can drive for a whole day on the same amount. Then hydrogen in the core ran out. The core contracted and heated up, and hydrogen began fusing in a shell around the core. Meanwhile, the core got hot enough, about 100 million degrees, to start fusing helium into carbon and oxygen. This is when things got weird. When helium fusion began, the star's internal structure changed dramatically. The energy production rate increased. The outer layers of the star expanded. Over the course of perhaps just tens of thousands of years, Stephenson 2-18 swelled from a relatively compact blue star to an enormous red supergiant. Its surface temperature dropped from 30,000 degrees to maybe 3,500 degrees. Its radius increased by a factor of 100 or more. Why does this expansion happen? It's a consequence of the way energy flows through a star. When the core contracts and gets denser, it generates more energy. But that energy has to escape through the star's outer layers. The outer layers respond by expanding, trying to radiate away all that energy. It's like blowing up a balloon. The more pressure you put inside, the larger it gets. But expansion has consequences. As the star's surface area increased enormously, it began to lose mass through powerful stellar winds. Remember, the surface gravity of these expanded stars is tiny. It doesn't take much to blow material off into space. Stephenson 2-18 is losing about 1 Earth mass every 6,000 years. Meanwhile, in the core, fusion continued through progressively heavier elements. After helium came carbon, then neon, then oxygen, then silicon. Each stage required higher temperatures and lasted for shorter periods. The silicon burning phase, the final stage before core collapse, might last only a few days. This is where Stephenson 2-18 is right now, somewhere in these late stages of fusion, burning through the last of its nuclear fuel. Its core is probably an onion-like structure, with shells of different elements being fused at different radii. The exact details depend on its mass, rotation rate, and other factors we can't precisely measure from 19,000 light-years away. Here's what will happen next, though the exact timeline is uncertain. It could be tomorrow, or it could be 100,000 years from now. Eventually, the core will be converted to iron. Iron is special because it's the most stable atomic nucleus. Fusing iron doesn't release energy, it consumes energy. When the core becomes iron, fusion stops. Suddenly, there's nothing to support the core against gravity. The core collapses. In less than a second, it goes from something roughly the size of Earth to something the size of a city. The protons and electrons in the atoms are crushed together, forming neutrons. The core becomes a neutron star, a ball of neutrons so dense that a teaspoon of it would weigh 1 billion tons. The collapse releases a staggering amount of energy, mostly in the form of neutrinos. These neutrinos blow outward through the star, and some of their energy is deposited in the overlying layers. A shock wave forms and propagates outward. When it reaches the surface, the star explodes. For a few weeks, Stephenson 2-18 supernova will be one of the brightest objects in our sky, possibly brighter than Venus, possibly even visible during the day. It will slowly fade over months and years, leaving behind an expanding nebula, and, at the center, either a neutron star or a black hole. That's the life cycle. From birth in a molecular cloud, to a brief period of stable burning, to a dramatic expansion, to a violent death. The whole story unfolds over about 5 to 10 million years, less than 0.1% of the sun's lifetime. And then it's over. The largest star in the known universe, gone in a flash of light. Now I want to bring this back to you. I want to talk about what Stephenson 2-18 means for your life, for your worldview, for how you see yourself and your place in the cosmos. When you look up at the night sky, you're seeing points of light. Some of them are planets in our solar system, reflecting the sun's light. Most of them are stars, like our sun, some closer, some farther, some brighter, some dimmer. To the naked eye, they all look roughly similar. Maybe some are different colors if you look closely, but they're just points of light. It takes a telescope and sophisticated instruments to reveal that among those points of light are objects so large they defy comprehension. Stephenson 2-18 is up there somewhere, invisible to your eyes, but real nonetheless. A ball of plasma so large that it would engulf Saturn's orbit. And you're here, a collection of atoms arranged in a pattern that can think and wonder and ask questions about the universe. The size ratio between you and Stephenson 2-18 is about the same as the size ratio between an atom and you. You're made of atoms, but you never directly perceive them. They're too small. In the same way, from Stephenson 2-18's perspective, if it could have a perspective, you would be inconceivably tiny, beyond invisible. But here's the thing. You can know about Stephenson 2-18. You can understand it, measure it, study it. Size doesn't determine significance. The tiny human brain can comprehend the largest star in the universe. That's extraordinary. Let me put this in personal terms. You are approximately 1.7 meters tall, give or take. You contain about 7 billion atoms. 7 nows and 27. You exist for maybe 80 years. In those 80 years, your sensory experience is limited to a tiny range of electromagnetic wavelengths, visible light, a small range of sound frequencies, a narrow temperature range, and the immediate vicinity of your body. And yet, through science, through mathematics, through the collective effort of humanity, you can know about objects that are 2 billion times larger than you, 19,000 light years away, billions of times more massive than anything you've ever touched, hotter than anything you've ever experienced, visible only through instruments you'll never personally use. That's the power of knowledge. That's the power of science. It extends your senses and your understanding far beyond the immediate limitations of your body. But there's something else, something more personal. When you truly comprehend Stephenson 2-18, when you really let it sink in how large it is, how far away it is, how we are able to know about it despite those challenges, it changes you. It gives you perspective. Your daily problems, your job stress, your relationship issues, your financial worries, they're still real and valid. I'm not saying they don't matter, but they exist in a context. The context is that you're living on a tiny planet orbiting an ordinary star in an ordinary galaxy. And out there in the universe are objects so large and so powerful that they make your entire world seem like a grain of sand on a beach. Some people find this depressing. They think it makes human life meaningless. If we're so small and the universe is so large, what's the point? But I think that's the wrong lesson to take from it. The right lesson is this. You exist in a universe capable of producing both you and Stephenson 2-18. A universe that contains both the smallest quantum fluctuations and the largest stellar giants. A universe with a range of scales spanning at least 45 orders of magnitude from the smallest to the largest things we know about. And somewhere in the middle of that range, made of atoms that were forged in stars like Stephenson 2-18's ancestors, is you, conscious, aware, capable of understanding the very cosmos that created you. That's not meaningless. That's a miracle. In 1990, the Voyager 1 spacecraft, at the request of astronomer Carl Sagan, turned its camera back toward Earth from a distance of 6 billion kilometers and took a photograph. In that photograph, Earth appears as a tiny pale blue dot, less than a single pixel. Sagan later wrote about that image. Look again at that dot. That's here. That's home. That's us. Every human who has ever lived on that dot. Every war, every love story, every discovery, every tragedy, all of it happened on that pale blue dot suspended in a sunbeam. Now imagine you could take a photograph from the Stephenson 2-18 system, looking back at Earth. We would be invisible. Not a dot, not even a pixel, just lost in the glare of the sun, which itself would be barely visible. From that distance, not only would you not see Earth, you wouldn't see our solar system. You might not even distinguish our sun from the countless other stars in the sky. And yet, from our pale blue dot, we can see Stephenson 2 to 18. We can measure it, study it, understand it. We've reached across 19,000 light years of space with our minds and our instruments, and we've touched something immense. That's the human story. We're small, but we're mighty. We're brief, but we're brilliant. We exist for a cosmic eye blink, but in that eye blink, we can comprehend eternity. Let me tell you about what's coming next, because the story of Stephenson 2 to 18 is far from over, and the future of astronomy is going to blow your mind. Right now, as I speak, there are several next-generation telescopes either under construction or in planning stages that will revolutionize our ability to study distant stars. The James Webb Space Telescope, launched in 2021, is already providing unprecedented views of the universe in infrared wavelengths. The Extremely Large Telescope, ELT, in Chile, when completed in the late 2020s, will have a primary mirror 39 meters in diameter large enough to see details on planets around other stars. These new instruments will allow us to study hypergents like Stephenson 2 to 18 in ways we never could before. We'll be able to measure their sizes more precisely. We'll be able to detect variations in their surface temperature, possibly even see convection cells on their surfaces. We'll be able to study the composition of the material they're ejecting into space. But more importantly, we'll discover new ones. Remember, we've only carefully studied a tiny fraction of the stars in our galaxy. There could be hypergents out there even larger than Stephenson 2 to 18, hidden in distant star clusters we haven't yet surveyed thoroughly. In 2022, astronomers using the Atacama Large Millimeter Array, ALIMA, discovered a star-forming region in the Milky Way that appears to be creating extremely massive stars, possibly stars that will eventually become hypergents larger than anything we've seen before. This region, known as G305, is about 12,000 light-years away and contains at least 200 massive stars in various stages of formation. The lead researcher on this study, Michael Burton from the University of New South Wales, suggests that some of these protostars might have masses exceeding 100 solar masses. If they survive their formation process, and that's a big if they could, eventually swell to become red supergiants that rival or exceed Stephenson 2 to 18 in size. But there's an even more exciting possibility. Some theoretical models suggest that in the early universe, when the first generation of stars formed, they might have been much more massive than anything we see today. These so-called population 3 stars might have had masses of 200, 300, maybe even 1,000 solar masses. If such stars existed, and if any of them expanded into red supergiants before dying, they would have been truly incomprehensible in size, possibly 3,000 or 4,000 solar radii. We'll never see those population 3 stars directly, because they all died billions of years ago. But we might see their supernova remnants, or detect their influence on the early universe through subtle effects on the cosmic microwave background radiation. And then there's the possibility of new types of stellar objects we haven't even imagined yet. Science has a history of surprises. Neutron stars were predicted theoretically, but seemed so weird that many astronomers doubted they could exist, until pulsars were discovered in 1967 by Jocelyn Bell Burnell. Black holes were considered mathematical curiosities until X-ray astronomy revealed them throughout the universe. What other exotic objects might be out there? Some theorists have proposed the existence of quark stars, objects intermediate between neutron stars and black holes, where matter exists in an even stranger state. Others have suggested Q-stars, or boson stars, held up by quantum pressure rather than conventional physics. Could there be stellar objects even larger than Stephenson 2 to 18 that we haven't discovered yet? because they don't fit our expectations of what stars should look like? It seems unlikely, but I wouldn't bet against the universe's capacity to surprise us. Here's what I'm really excited about, though: the possibility of directly imaging these Hypergent stars. Right now, even with our best telescopes, Stephenson 2 to 18 appears as essentially a point source. We can measure its size through indirect methods, but we can't actually see it as a disk with surface features. But future instruments might change that. The proposed Habitable Exoplanet Observatory, HabEx, or the Large Ultraviolet Optical Infrared Surveyor, LAVOIR, if they're ever built, would have the resolution to potentially see the largest hypergents as actual disks. We might be able to see their surfaces, watch them pulsate, observe storms or eruptions on their photospheres. Imagine that. Imagine watching a live feed of Stephenson 2 to 18's surface, seeing features larger than our entire solar system evolve and change in real time. It would be like the first time we saw close-up images of Jupiter's Great Red Spot or Saturn's rings. Transformation from abstract knowledge to visceral, visual reality. And beyond just looking at these stars, we're getting better at understanding them theoretically. Modern supercomputers can simulate stellar evolution in incredible detail. In 2019, a team led by Selma de Mink at the University of Amsterdam ran simulations of massive star evolution that revealed new insights into how stars lose mass, how they rotate, and how they interact with binary companions. These simulations are getting sophisticated enough that we can model individual stars. We can take what we know about Stephenson 2 to 18, its mass, luminosity, temperature, composition, and run detailed computer models of its interior structure. We can predict how it will evolve over the next 100,000 years. We can estimate when it will go supernova and how bright that supernova will be. Of course, the models have uncertainties. Stars are complicated. There are processes happening inside them that we don't fully understand: convection at extreme scales, magnetic field generation and evolution, mass loss mechanisms. Every time we improve our observations of real stars, we find something that challenges our models and forces us to refine them. But that's the beauty of science. It's not about having all the answers. It's about asking better questions and constantly refining our understanding. The future of studying hypergents is bright pun intended. We're going to learn so much more about these objects in the coming decades. And every new discovery will raise new questions, opening up new areas of investigation. That's the never-ending story of human knowledge. Each answer leads to new questions. Each boundary we push reveals new frontiers beyond. Now I want to get philosophical with you, because Stephenson 2 to 18 raises questions that go beyond just astrophysics. Questions about existence, scale, meaning, and our place in the cosmos. Let's start with the obvious. What does it mean to exist at such different scales? You are a human being. Your experience of reality is shaped by your size. You can hold a coffee cup, climb a mountain, look at the sky. These experiences are possible because of your scale. You're large enough that quantum effects don't dominate your existence, but small enough that you're not ripped apart by tidal forces or crushed by gravity. Stephenson 2 to 18 exists at a completely different scale. It doesn't experience anything, of course, it's not conscious. But if we imagine what existence at that scale would be like, it's completely alien to our understanding. Time would flow differently. The concept of surface would be ambiguous. Gravity would be simultaneously negligible at the surface and overwhelming at the core. There's a philosophical principle called the mediocrity principle, which suggests that our position in the universe isn't special. We're not at the center of the solar system. Copernicus showed us that. We're not at the center of the galaxy. Our galaxy isn't special among galaxies. Even our universe might not be special if multiverse theories are correct. But when it comes to scale, we actually are kind of special. We exist at roughly the geometric mean between the smallest and largest scales in the universe. The Planck length, the smallest meaningful distance in physics, is about y minus 35 meters. The size of the observable universe is about yd meters. A human being, at about 1 meter, sits roughly in the middle of that range on a logarithmic scale. Is that a coincidence? Some philosophers and physicists think it might not be. There's an argument that conscious observers can only exist at intermediate scales, because both quantum effects and relativistic effects make consciousness impossible at extreme scales. This is a form of the anthropic principle, the idea that the universe must be capable of producing observers, because we observe the universe to exist. But here's where it gets weird. Stephenson 2-18 pushes the boundaries of the large-scale limit. It's nearly as large as stars can possibly get before they become unstable. It exists at the edge of possibility. And we, tiny beings on a tiny planet, can perceive it and understand it. We can reach across the scale spectrum and touch both the very small through particle physics and the very large through astronomy. That's not physically reaching, of course. But intellectually, mathematically, scientifically, we can comprehend things at scales far beyond our direct experience. We're the universe contemplating itself. Carl Sagan famously said, "We are a way for the cosmos to know itself." When you think about Stephenson 2-18, you are engaging in self-reflection on a cosmic scale. You are atoms that were once inside stars, like Stephenson 2-18's predecessors, that have organized themselves into a pattern capable of understanding the very stars that created them. Let me put this another way. The atoms in your body are about 13.8 billion years old as the universe itself. They've been on a journey. They started in the Big Bang as simple hydrogen and helium. They were pulled together by gravity into the first stars. Inside those stars, they were fused into heavier elements. When those stars died in supernova, your atoms were scattered into space. They were incorporated into new stars, maybe several generations of them. Eventually, they became part of a molecular cloud that collapsed to form our sun and solar system. They ended up on Earth. They became part of the ocean, the atmosphere, rocks, primitive life, complex life, and eventually you. Your atoms have been on a 13.8 billion year journey through the cosmos, and they have somehow organized themselves into a configuration that can contemplate their own history. That's profound. That's staggering. And it's all possible because of stars. Because stars forge heavy elements and distribute them through space when they die. Without stars like Stephenson 2-18's ancestors, you wouldn't exist. There wouldn't be carbon for your DNA, iron for your blood, calcium for your bones. So when you think about the largest star in the universe, you're not just thinking about something distant and alien. You're thinking about a cosmic relative, a member of the same process that created you. You and Stephenson 2-18 are part of the same story, the story of the universe creating complexity, creating structure, creating beauty. Some people find this connection humbling. Others find it empowering. I find it both. It's humbling because it shows how small and brief we are. But it's empowering because it shows that we're part of something much larger and longer lasting than our individual lives. When Stephenson 2-18 goes supernova, and it will, someday, it will scatter its elements into space. Those elements will become part of new molecular clouds, new stars, new planets. Maybe billions of years from now, some of those atoms will become part of a new form of life on a planet we can't even imagine. And maybe that life will look up at its sky and wonder about the stars, just like we do. In this way, the universe perpetuates itself. It creates, destroys, and recreates in an endless cycle. And consciousness beings like us, who can wonder and question and understand, emerges from this cycle, allowing the universe to know itself. That's not just physics. That's poetry. We've come to the end of our journey, and I want to leave you with some final thoughts about what all of this means with the largest star in the universe, tells us about reality, about ourselves, and about the future. First, let's acknowledge the sheer audacity of what we've done as a species. We are hairless apes who evolved on an African savanna to hunt, gather, and survive in small tribes. Our brains evolved to track animals, recognize faces, throw rocks accurately, and cooperate in groups. Nothing about our evolutionary history prepared us to understand things like Stephenson 2 to 18. And yet, through the collective effort of thousands of scientists over hundreds of years, through the development of mathematics, physics, engineering, and astronomy, we've managed to not only detect a star 19,000 light years away, but to measure it, understand it, and place it in the context of stellar evolution and cosmic structure. That's insane. That's impossible. And yet, we did it. Every time you look up at the night sky now, you'll know that somewhere up there, invisible to your eyes, is an object so large that it defies human comprehension. You'll know that light which left that star's surface when humans were still living in small hunter-gatherer bands is arriving at Earth right now. You'll know that someday, perhaps tomorrow, perhaps 100,000 years from now, that star will explode with such violence that it will briefly outshine entire galaxies. And you'll know that you are made of the same stuff as that star. You are stardust, assembled by evolution into a pattern that can think and feel and wonder. You are the universe examining itself. But beyond the poetry and philosophy, there's a practical message here. And it's this: never stop pushing the boundaries of knowledge. Every time we think we've found the limit, the biggest star, the oldest galaxy, the most distant object, we discover something that pushes that limit further. The universe is always more vast, more strange, and more wonderful than we imagine. When the first telescopes were invented in the early 1600s, people were amazed to discover that the moon had mountains and that Jupiter had moons. These discoveries revolutionized our understanding of our place in the cosmos. Today, we're discovering hypergents and exoplanets and gravitational waves. What will we discover next? I don't know. Nobody knows. That's what makes it exciting. But here's what I'm confident about. There are kids watching this video right now who will grow up to be the astronomers who discover even larger stars, or who develop the theoretical frameworks to understand them better, or who build the next generation of telescopes that will reveal new cosmic wonders. Maybe that kid is you. Maybe you're the one who will discover something that makes Stephenson 2 to 18 look small by comparison. Maybe you'll be part of the team that finally watches one of these hypergents go supernova in real time. Maybe you'll develop a new understanding of stellar physics that revolutionizes our knowledge. Or maybe you won't go into astronomy at all. Maybe you'll be a doctor, or an artist, or a teacher, or a builder. That's fine too. But I hope that learning about Stephenson 2 to 18 has changed you in some small way. I hope it's given you a sense of wonder, a sense of perspective, a sense of the vastness and strangeness of the cosmos we inhabit. Because ultimately, that's what this is all about. Not just collecting facts about stars, not just measuring and cataloging and calculating. It's about expanding our sense of what's possible. It's about pushing back the boundaries of ignorance and fear with the light of knowledge and understanding. In 1977, NASA launched the Voyager spacecraft with golden records attached messages to any alien civilizations that might find them in the distant future. These records contained sounds and images from Earth, music, greetings in different languages, photographs of humans and our planet. They were messages in bottles, cast into the cosmic ocean. In a way, every telescope we build, every observation we make, every discovery we publish, these are all messages. Not to aliens, but to the future. We're saying to our descendants, we were here, we looked up at the stars, we wondered and questioned and sought to understand. We found this amazing, impossible, beautiful universe, and we did our best to comprehend it. Stephenson 2 to 18 is part of that message. It's evidence that we live in a universe of extremes. A universe that can produce objects so large, they challenge the boundaries of physical possibility. It's evidence that we've developed the tools and knowledge to detect and understand these objects despite the vast gulfs of space that separate us. And it's evidence that we care. We care about truth. We care about understanding. We care about the universe beyond our immediate surroundings and our immediate needs. That caring, that curiosity, is perhaps the most fundamentally human thing about us. It's what separates us from all other known life in the universe. As far as we know, we're the only species that looks up at the stars and asks, "What's out there?" We're the only species that builds telescopes and satellites and sends spacecraft to other worlds. We're the only species that writes 160-minute YouTube scripts about the largest known star. That's our gift and our burden. We're cursed with curiosity and blessed with the intelligence to satisfy it. We're doomed to always have more questions than answers. But we're also empowered to constantly expand the sphere of our knowledge, pushing back the darkness of ignorance with the light of understanding. So here's my challenge to you. Keep looking up. Keep asking questions. Keep learning. When you feel small and insignificant, remember that you're made of stars. When you feel overwhelmed by the vastness of the cosmos, remember that your tiny human brain can comprehend that vastness. When you feel hopeless about humanity's problems, remember that we're a species that can detect and measure stars 19,000 light years away. If we can do that, we can solve our problems here at home. The story of Stephenson 2 to 18 is still being written. We don't know when it will go supernova. We don't know if there are even larger stars yet to be discovered. We don't know what future observations will reveal about its structure, its evolution, or its fate. But we'll keep watching. We'll keep measuring. We'll keep learning, because that's what we do. That's what makes us human. And someday, maybe thousands of years from now, maybe millions, our descendants will look back at this moment, this brief period in cosmic history when Stephenson 2 to 18 was the largest known star, and they'll smile at how little we knew. They'll marvel at how primitive our telescopes were, how crude our measurements, how incomplete our understanding. But they'll also recognize that we were part of an unbroken chain of curiosity and discovery that stretches from the first humans who looked up at the night sky and wondered all the way to their present moment, wherever and whenever that might be. We're all stardust, pondering stars, in a universe that somehow produced both the largest stellar giants and the consciousness to contemplate them. That's not just science. That's not just astronomy. That's the most profound story in the cosmos. And you're part of it. Thank you for joining me on this journey through space and scale, through physics and philosophy, through numbers so large, they lose meaning, and implications so profound, they change how we see ourselves. I hope Stephenson 2 to 18 has expanded your mind, challenged your assumptions, and given you a new appreciation for the strange and wonderful universe we inhabit. If you enjoyed this deep dive into cosmic extremes, please hit that like button, subscribe to the channel for more mind-expanding content, and let me know in the comments, what aspect of Stephenson 2 to 18 blew your mind the most? Was it the size? The mass loss? The eventual supernova? The philosophical implications? And one more thing, the next time you look up at the night sky, take a moment to really think about what you're seeing. Those points of light aren't just decorative. They're distant suns, some of them hundreds or thousands of times larger than our own sun. Some of them are dying, some are being born. And among them, invisible to your naked eyes, but real nonetheless, is Stephenson 2 to 18, the largest known star in the universe, a cosmic giant that exists at the very edge of what physics allows. You are alive at precisely the right moment to know about it. That's extraordinary. That's a gift. Don't waste it. Keep looking up. Keep asking questions. Keep seeking truth. The universe is vast and strange and beautiful, and you're part of it.